So this is the last subject that we're going to talk about in our class, and I just wanted to make sure and cover this. Those of you who are going on to things like some psych stats or anything, any other stat class, very well may see this chi-square procedure. So I wanted to make sure and show it to you. I found a little meme, a little joke. It says not chi square, never chi square, always chi-square. So that's how this is pronounced. So basically, what this is going to be is we're going to be doing inferences about frequencies now, frequencies of categorical and qualitative data. So let's talk first about this chi-squared distribution. And the chi-squared looks like this. This is the Greek letter chi, which basically looks like an X, a big capital X squared. And it is made up of the sums of squares of normal distributions. Okay, this is just kind of the background in it. This isn't really something that we're going to need to do anything with. Just some facts about it. Of course, the total area is 1 because this is a probability distribution. It actually starts at 0. There's no negative answers because, of course, it's made up of z squareds. And then it goes out to infinity. It's right skewed, as you can see. But as the degrees of freedom gets higher, and its mean is its degrees of freedom. So like chi-squared of 5, its mean is actually right here. So, and then chi-squared 10, its mean is here. And you can see what happens as you have larger. So this is chi-squared 19. You can see how this gets closer and closer to normal because we want it to be right there to be normal, where the mean is the same as the median and the mode. So this is what it kind of looks like. And it is it's used for actually quite a few things. What we're going to use it for is goodness of fit tests. So a goodness of fit test it sounds kind of a weird thing, like what are we doing? But what we're talking about is, like I said, qualitative or categorical data. Maybe ethnic origins, cars by color, M&Ms. We're definitely going to talk more about M&Ms because you know how I like to talk about M&Ms. And these have distributions that are an extension of the binomial distribution called the multinomial distribution. So instead of a yes or no answer that we had in binomial, we now have more than 2 possibilities. We have green, red, and blue, or something like that. So now we have 3 possibilities that we're talking about. And each one of these has a probability. And so essentially what we're doing is we're basically doing an extension of the proportion, the test for 2 proportions in a way. So we're kind of doing an extension of this. So instead of a test for 2 proportions, now we have more than 2 proportions. So a few things that it has to happen. We have to have n identical trials. So we have to try, am I going to get green, blue, or red? Each trial has one of these categories. It either has to be green, blue, or red. Okay, what I'm looking at can't be anything else besides green, blue, or red. So if we say, marbles in a bag or whatever, the probability the outcome falls in a particular category I on a single trial is P sub I and remains constant from trial to trial. And all the probabilities equal 1. So let's say that I do have some marbles in a bag. So I have some marbles in a bag. And we'll say, for the sake of the argument, I have 2 blue, 3 green, and 1 red marble in my bag. So the probability of getting a red marble is 1/6. The probability of getting a blue marble is 2/6, and the probability of a green marble is 3/6. And so this is 1/3, and this is 1/2. And so these probabilities add up to 1. And if we were to repeatedly take a marble out of here and replace it, so we're going to sample with replacement. That's really important. Then the probability would be the same from outcome to outcome. So what we do is we're now going to do the experiment. So let's say we reach into this bag, I don't know, we gotta do it a lot. So let's say at least 50 times. So we reach into this bag 50 times. And when we reach into this bag 50 times, let's say that we get, how many greens? Let's say we got 29 green. I should probably write that in green, huh? So we got 29 green. And then we got, let's see. What's that about? 17 blue. And then what would be left here? Let's see. Then we'd have what? 6. So only 6 left? No. 4. See, that's 47. The 46. I think it's 4. Yeah. 4 red. Okay, so if we do this 50 times, we're going to see if 29 green, 17 blue, 4 red. Now, we're told this is what the bag looks like. And we're going to try to see, well, are you guys pulling a fast one? Is this really what the bag is? Is it really 1 to 2 to 3? That's the question. And so now, and these are our observations. This is 01, 02, 03. So those are observations, and you notice that 29 plus 17 plus 4 equals 50, or I hope it does, because yes, I think it does. Okay. So binomial versus the multinomial experiment that we're doing. So binomial was just a special case of the multinomial with just 2 categories. We had success and failure, p and 1 minus p, x and n minus x. And we made inferences about p. But now we have more. We have more probabilities now to look at. So let's talk about setting up a goodness of fit test. We can either be testing whether all of the proportions are equal. So this is if we assume that everything is equal, we would do this test. Or we can test any proportions as long as they add up to 1. So let's see if, let's do our example and see if P1 is truly 1/2, P2, or, well, here, I'll even make this easier. So P green is equal to 1/2, and P blue is equal to 1/3, and P red is equal to 1/6. And our alternative hypothesis is just at least 1 P is incorrect. And it's weird. We don't say these are not all equal. We just say at least 1 is off, which actually in this case with 2 would have to be off because, of course, they're dependent on each other. Because this last one is 1/6, because this is 1/2 and 1/3, right? It has to add up to 1. So at least 1 P is incorrect, which really is, like I said, at least 2 are. So in order to do this test, we have our chi-squared statistic. Now, like we said, we have some preconceived idea about the values of P. We think we know what the makeup of the marbles are in our bag. We're not sure. The expected number of times that outcome will occur is E sub I equals N P sub I. Okay, so expected number. So how many green did we expect out of 50? That means that our expected number for green is 50 times 1/2, or 25. Whoops. That was our expected number of greens. What's our expected blues? Would be 50 times 1/3, which would be what? Some reason my brain's not working today. Let's do 50 divided by 3 is 16.67. So this is 16.67. And then finally, we want the red ones. Oops. So E of the red is 50 times 1/6, which, let's see, 50 divided by 6 is 8.33. So these are our expected amounts. So we have our expected values right here. So the question is our observed values, which were what? What were our observed values? 27, I gotta remember. 29, 17, and 4. Okay. So we actually got 29, 17, and 4. Now, could this difference be just by chance? Or could it be that that is not really the makeup of the marbles in the bag? So which is it? And that's when we do our hypothesis test. So if these are too far away from these, we're going to reject the null hypothesis and say, I don't think these probabilities are correct. But if these are close enough to these numbers to be just by chance, we'll say, okay, they could be right, and we won't worry about it. It looks right. I mean, that's all we can say, right? Okay, so here's the chi-squared statistic. So I'm going to do this one we just did. I'm just going to do this by hand. So it's the sum of 29, which was our observed value, minus 25, squared, divided by 25, plus, then we're going to take our next one, which was 17 minus 16.67, divided by 16.67, plus, and for the last one we had 4 minus 8.33, forgot the squared, divided by 8.33. This is going to be our test statistic. So let's see, that's 4 squared is 16 divided by 25, plus, let's see, that's going to be 17 minus, that's 0.33 squared divided by 16.67, plus, let's see, that's going to be negative 4. That's going to be 4 point, doesn't it matter? Because I'm going to square it anyway. Squared divided by 8.33. Okay. We get a chi-squared of 2.897. Okay. So, when the null is true, these differences, O minus E, will be small. So their squares will be small, right? But when they're big, the squares will be big, make this number big, which pushes it, if you look at a chi-squared distribution, pushes it way over here. If the numbers are big, it pushes it here. And remember, our p-value is going to be the area in the tail of the chi-squared distribution. So what is ours going to look like? So for our experiments, we're going to base our degrees of freedom on k minus 1. K is the number of the p's. So we have only 3. It can be green, blue, or red. So we have 3 minus 1 is 2. So we're going to do a chi-squared with 2 degrees of freedom. So how do I find this p-value? Well, on your calculator, you have under distributions, you have chi-squared CDF. So our lower is going to be our actual number because we want the right tail, because we want this tail right here. So our lower number is actually going to be, it's actually here, I think, 2.897. So let's put 2.897. And then our upper, 9999 degrees of freedom, is 2. Paste. Enter. Looks like our p-value, whoops, sorry. Our p-value is equal to 0.235. So we would do just like we do before. We do not reject the null. We do not have the evidence to conclude that the probabilities are incorrect. So we go back and go, okay, well, it looks like those probabilities could be the right answers. It could be 1/2, one. It's probably right. We have no reason to think that it isn't. Okay, so let's talk about how we do this on the calculator. So many of you, some of you, and here's where a problem is going to come around. Some of you will have this test on your calculator called the chi-squared GOF test. Some of you do not have this. And the way that we're going to be doing this is you're going to put your observed and expected values in lists 1 and 2. Your observed values will go into list 1. Your expected values will go into list 2. You will basically fill each line up with NPI. This may be the same and it may be different. I'll go into more detail in just a moment. And then we go to stat, test, chi-squared GOF test, and we fill in where we put our observed, where we put our expected, degrees of freedom is k-1, and we calculate. You have to tell it k-1. There are times when it isn't. For our class, the experiments that we're going to be doing, we're going to be using that. Okay, so those of you who do not have a specific test that says GOF, it does not, if you have chi-squared that does not say GOF, then you do not have the goodness of fit test. You're going to have to do it kind of by hand, but kind of on the calculator. Again, we're going to do these first 2 steps are the same, entering our observed and expected values. Then we're going to make this one L1 minus L2 squared, making sure we put parentheses in there. And then list 4, and we could make this in one list also. We're going to take list 3 divided by list 2. So then list 4 is what we need. So we want to do a 1 var stat, and we can get our sum of our x's. So we just do a 1 var stat on list 4 and look for sum of the x's. That's our chi-squared statistic. And then we're going to go back and do what we just did, chi-squared CDF under the distributions menu. We're going to use the chi-squared value we have to 999 with k-1 degrees of freedom. Or when it says lower, you put your chi-squared. You put your chi-square value. Okay, upper 9999 degrees of freedom, k-1. So now we're going to use our p-value that we get from here to make our decision. So let's do this example. So let's say we have a bag with 54 M&Ms. I got lazy and didn't write all of M&Ms there. We have 12 green, 7 red, 10 yellow, 14 brown, 5 blue, and 8 orange. The company insists the proportions are equal of all colors of M&Ms. Can we prove them wrong? So, let's see. P1 equals P2 equals P3 equals P4 equals P5 equals P6 equals 1/6. and at least one p is not equal, which would make two of them have to be, right? Okay. So the first thing that we do is here is our observed values. Here is our expected values. And the expected values I got because we had 54 M&Ms, this was N, times each P, which each P was 1/6. So it made it 9. So let's go over here and go to our lists. And in our first list, we're going to put in our observed values. Put this over the other side. There we go. 12, 7, 10, 14, 5, 8, and then in list 2, gotta clear my list real quick. Oops, clear. Here we go. We're gonna put in all 9s. 1, 2, 3, 4, 5, 6. Okay, so then list 3, clear this out. List 3, for those of you who do not have the goodness of fit test, list 3, we're going to go parenthesis, list 1, whoops, my list 1 didn't go, second 1 minus second 2, and square it. Whoops, I hit the wrong button, square it. Okay, and then list 4 is going to be list 3 divided by list 2. Okay, so here's all of those. Now what I'm going to do is I'm going to go stat, calc, 1var stats on list 1. Frequency list should be blank. And I look at my sum of the x's. So my sum of the x's is 56. That is my chi-squared value. And now I go distributions, go to number 8, which is chi-squared CDF. My lower is 56 to 9999. My degrees of freedom is k, 1, 2, 3, 4, 5, 6, minus 1, so 5. And paste. And I get, ooh, that's a very small p-value. Okay, so my p-value is 8.12 times 10 to the negative 11th, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ooh, that's a tiny p-value. So we would definitely reject the null. We have enough evidence to conclude that the proportion of M&Ms is not all equal. M&M colors, I should say M&M colors. And I should say are, because that would be more correct, are not all equal. Okay. So real quick, now I'm going to back up just a minute and I'm going to talk about if I have a goodness of fit test. So if I have that goodness of fit test, I can go straight to tests. And you see this thing that says chi-squared GOF. You have to make sure you do the GOF one and hit enter. My observed values I put in list 1. My expected values are in list 2. My degrees of freedom is 5, just like I wanted it to be. So put that there. Sometimes you have to put it in. Hit calculate. And we got a completely different answer. What the heck happened? Okay, let me pause for a second. Okay, backing up again. Okay, what I had done before, when I did this, when I did my 1var stats, I accidentally used list 1 instead of list 4. So very, very important. I'm not going to re-record this because I want you guys to see how easy it is to make that mistake. So list 4, make sure that's the frequency list and hit calculate. And the sum of my x is now 6.22, or That is my chi-square value. So now what I want to do is now I'm going to go to distributions, go to number 8, chi-squared, and now this is 6.22. And now when I paste this, it won't be so tiny. Okay. Now my p-value is 0.285, which completely changes my, so now I would not reject the null. And we do not have sufficient evidence to conclude that M&M colors are not equal proportions. Okay. So again, now, if I was going to do this using the goodness of fit test, which, I mean, admittedly, I'd be less likely to make a mistake on, I go up here, I hit the up arrow, chi-squared goodness of fit. Now I make sure it's list 1 and list 2, because those were the observed and expected. And I hit calculate, and it gives me my chi-squared, it gives me my p-value, and this CNTRB, in case you're wondering what that is actually a list of each one of the O minus E's squared over the E's. So this 1 is the first one, because 12 minus 9 is 3, 3 squared is 9, 9 over 9 is 1. And so on and so forth. So this actually gives you now a list of these numbers, just so you can have them. Okay, so let's go on to the next one. So a couple of things. Notice that chi-square only has an approximate chi-square distribution, this test statistic. For this approximation to be accurate, each one of the expected cells has to be greater than or equal to 5. If one of them is less than 5, you really do need to do some corrective stuff with it. You need a bigger sample size. You need something. Something needs to change. And the other thing is, we do this a little bit differently than tests. Now, a lot of times when we're doing hypothesis tests, we're trying to prove that other thing is true. We're trying to prove that the alternative is true. Here, we're still trying to do that. We're trying to see if we have enough evidence to prove the alternative, but we're really trying to see if we just we have enough evidence to say our model is wrong. Because we don't want to have enough evidence to say our model is wrong. But if we do, we do. So it is a little bit different in that most of the time you're wanting not to reject. Whereas other tests, you're like, yay, I rejected, so I get to prove something. Now you're like, oh, good, my model is working. So it's a little bit different. So let's talk a little bit about contingency tables. And so remember, chapter 4, I know you probably have nightmares from it. We have 2 categorical variables. We might have the immigration and the country of origin. Remember those? Vehicle type and country North America. Don't know if you remember that one. Gender and handedness. Oh, we're doing that one. And then salmon and Alaska location. That was test 1, by the way. So what we're going to concentrate on is the gender and handedness example. So we have people are right-handed or left-handed, male or female. And I actually had to aggregate a few classes in order to get this high enough. My sample size wasn't high enough because male left-handeds, the expected amount was too much less than 6, and or too much less than 5, and I had to get it over 5. So I actually managed to do it. It took me a minute. Okay, so testing for independence. So we want to see if handedness is independent of gender. Or is one gender more or less likely to be left-handed? So now before, what we did is we did a probability table. We tried to see if the probability of A intersection B was equal to the probability A times the probability of B. I know you'd be too far past this. But, sometimes you say, well, are these close? Are these close enough? Are they considered statistically significant? It's hard to get them exact with a sample. So one of the ways we can do this is using an hypothesis test. And this is one of the weird hypothesis tests. Classifications are independent. Well, here's your equal sign right here. Or the classifications are dependent upon each other. So we're going to consider them independent unless we can prove they are dependent on each other. So let's go on and do that. So this is how we test. Now we have our observed. This is just like the other one. We have our observed. So we have this sample of 85 individuals, 31 males, 54 females, 70 right-handed people, 15 left-handed people. And we have these OIJs. See, the difference is this is O11, this is O12, this is O21, and this is O22. So these are our observed values inside here. And then the expected. Okay, now how do we figure out what we expect this to be under independence? Well, we look at these totals on the outside and we say, well, if the null is true and these are independent, then what should these numbers inside here be? So this would be 70 out of 85. So here's what I've done here. 70 over 85 times 31 out of 85 would have to be equal to a certain count over 85, right? Because the probability that somebody was right-handed times the probability someone is male has to equal the probability someone is a right-handed male in order for it to be independent. But to figure out what this number is, we just multiply 85 to both sides, which cancels out one of these. So we just have 70 times 31 over 85. And that's exactly what each one of these is. So this right here is, you can figure it out for yourself, 70 times 31 divided by 85. So 25.53, which is exactly what we got. And so we would do this with each one of these. So for this one is 15 times 31 over 85. This one is 15, so you just take this total and this total. 15 times 54 over 85. And this one is 70 times 54 over 85. So that's how you find out what they're expected. If they're independent, this is the numbers that we would expect. Of course, we're not going to get these counts exactly because it's impossible. But how close are these to this? And it's pretty darn close. I don't know. They look pretty close to me. So I would probably call this independent, right? Just by even just eyeballing it. But let's do the test. So we do our chi-squared by, again, we take the difference between 25 minus whatever it was, 25.53 squared over 25.53 plus the rest of them. We would do all of them that way. And that's what our chi-squared would be. Now, our degrees of freedom is the number of rows, and that's the rows in our inside. So the number of rows, 2 minus 1. The number of columns, I have 2. So our degrees of freedom is 1 times 1 is 1. So this is the chi-squared test that's in your calculator, which is really nice. Your calculator does this. But before you go to it, you have to enter this into a table. You have to enter the middle of your table as a matrix. So I'm going to show you guys how to enter a matrix. So first step is we go second x negative 1. That brings up our matrices. Now we're going to go over to edit. So we want to edit a matrix. We're going to choose matrix A, enter. Now I want the number of rows and the columns. Again, not including the totals. So 2 by 2. Now I just have zeros, so I'm going to plug these in. 25 and 45, 6, and 9. So now that this is done, I'm going to quit. So quit is second mode. And I wrote that right in here. Hang on. And quit. You got to quit out of that. So now we're going to use chi-squared test. So we're going to go stat, tests, go to chi-squared test, not GOF, where it says chi-squared test. Hit enter. Now, observed matrix A. Now, if your matrix A is not defaulted there, to get that matrix there, you're going to go back to this. So second x negative 1. And under names, keep it at names and just hit enter. And that'll bring it there. Expected default is B. It's going to put it doesn't have to be full yet. It's going to put our expected matrix right there. We don't have to calculate it ourselves. And we're just going to hit calculate. And this gave me a chi-square value of 0.098. I knew it was going to be small. And a p-value of 0.754. Yes, big p-value, I know. We have a degrees of freedom of 1. So we see that we have a very small chi-square value, a very large p-value. So do not reject the null. We do not have any evidence to suggest that handedness and gender are dependent. So now normally like I said, we never conclude a null hypothesis. Chi-squared tests are a little bit different in that we kind of can in this case. I mean, we have no reason to think they're dependent on each other, so we could call them independent for the purposes of whatever we were doing after this. So, okay, and that's the results. We talked about that. Here's a couple assumptions. Of course, the cell counts have to satisfy the conditions of our multinomial experiment. So each one of these cell counts has to be independent, right? It can't be like male versus female versus whatever we have. The expected cell counts have to be equal to or greater than 5. And if we don't have that happen, we can either choose a larger sample size or combine cells. Sometimes that has to be done. And that is the last video. I'm so glad that you guys stuck it out with me. Thanks for watching all these wonderful videos. I always try to make them better, a little bit better. I was just fixed these. They were really, really old, so I made all new ones this year. If there's any issues with them, please do, kind of let me know for the future so that I can fix anything. And we had a great semester. Thanks.